Okay, now I'm going to reintroduce you, Laura. So this is Laura Boucheron, who's she's an associate professor at New Mexico State University, and she received a bachelor's and master's degree from the Clip School of Electrical and Computer Engineering and at NMSU, and a PhD from UC Santa Barbara. She's going to be talking on curricular academic analytics and electrical engineering at NMSU. Next week, Yiming is going to be talking about learning outcomes graph optimization. And so we'll get an abstract out to you, and we're going to be putting a web page together where we can post these talks and materials associated with these going forward. And so the next week's talk is Yiming will get that out to you early this week. You all are welcome to attend any of these, and it's always at this time on this channel. So with that, I'm going to turn it over to you, Laura.
Great, thank you very much, and thank you for inviting me here to talk to you today. So a lot of this work was actually inspired by Greg's work and his collaborators' work. And so I'm here to kind of talk about some of the ongoing efforts that we have here at NMSU. Tony, John, and Irving have introduced themselves. They are all students who are either currently working with me or will be working with me on some of these aspects associated with this analysis. So I changed my topic slightly. I said I'd talk about three things. I'm going to talk about three things. The first of those three things is a little bit different when I sat down to kind of look at what went together the best. First, I'm just going to give a really brief overview of what our Bachelor of Science in Electrical Engineering looks like at NMSU, since that is the structure that's going to drive a lot of the subsequent analyses. Won't go into the gory details, but kind of establish what it is that our degree looks like and how that informs some of the analyses that we do. Then there's three main ongoing topics that I want to kind of talk a little bit about in terms of some of the results that we've gotten. The first is what changed from the abstract that I sent to Greg. And what we're going to talk about here is the students who progress through our degree program. What do their schedule complexities look like compared to the curricular complexity associated with a canonical degree roadmap? The second two topics are very interrelated. They use essentially the same data, so I'll kind of talk about them together. And that is, given our core courses in our BSEE, is there any correlation in student performance between pairs of courses? Then I'm going to look at how did those pairs of courses relate if we were to start to look at how many topics are dependent between these pairs of courses. So we're kind of looking at a grade correlation between our BSEE core and then a topic level dependency. So let me first just give you a really brief overview of our BSEE degree. So here's kind of a graphical representation. We were the first engineering curriculum at NMSU to reduce our curriculum to 120 credit hours. You see it's crept up a little bit since then. That was in 2016, I believe. So it's crept up a few credit hours since then. But this was the work of the committee really trying to get us back down to a degree that could potentially be finished in 4 years. I think we took it from 132 down to 120, so it was quite an effort. The variance in total number of credits has to do with variance in some of our elective choices in the different specializations. Now, really what I want to call your attention to is I've kind of categorized these in terms of our EE core, and I'm sorry I don't have a better, more obvious pointer, but our EE core is kind of this salmon color. So these are the EE courses that every single BSEE student takes. We have the engineering core. All of our BSEE students must take these, but they are also taught to other engineering disciplines, mechanical, industrial, civil. We have the math core. Some of these are actually taught in electrical engineering. So this linear algebra prob and stats course is actually taught in EE, so is the multivariate and vector calculus. But we characterize these as mathematic core courses. The blue are our science core, the light blue. The dark blue are our STEM courses. These can be specified by the concentration. So some concentrations say for your STEM electives, here's a choice of courses to take. And then we have the gen eds. Now I kind of have a key over here to the right. So the single star in the next topic, when we're talking about schedule complexity, those are the courses we're going to focus on. So we're focusing on basically the STEM core of the BSEE degree. The gen eds have very small contribution to curricular complexity, are widely offered plenty of options for students. So we're really going to focus on the courses that can tie up students in terms of degree progression a bit more. The EE core, these salmon colored ones, in the second part of my talk are going to be what we focus on. These are the EE core courses. Those are the courses that I and my colleagues can control in terms of prerequisite structure topics within them, the potential for curricular redesign. So let me get into the first of three analyses that we have done here. And in this, what we're looking at is related to curricular complexity. And again, this was largely motivated by Greg Heilman's work. And also noticed that this and several other results associated with this was just accepted to the 2021 FIE conference. So there will be more details forthcoming in that paper. I'm sure you all are probably an audience that doesn't need the details of this, but let me run through really quickly these terms and factors that we're using here. So course cruciality, taken from the curricular analytics literature, is a measure of how crucial the course is, has to do with its blocking factor, which is how many courses does this course block. You know, it's a prerequisite either directly or through a string of prerequisites. And DI is the delay factor, which is the length of the longest path, which is going to largely control how long you can potentially get through the curriculum. Both of these contribute to this concept of course cruciality. So the larger the blocking factor is, the more courses it blocks, the more crucial it is. The longer the longest path is, the more crucial it is. I should note, and Tony and I didn't notice this until we were trying to get the FIE paper submitted. We're using longest path in a graph library in Python called NetworkX, which actually results in a number 1 less than the way it was defined in Heilemann et al.'s work. So add 1 to everything. We're going to be comparing them to each other. And so, you know, relatively speaking, the results in our processes will be similar. So the curricular complexity is the sum of the crucialities of all of those courses. Now, again, motivated by the work and used in some other context within Heilemann et al., some other people who have worked on similar things, but we explicitly define separately are this term-weighted course cruciality. So we're just multiplying the cruciality by the term in which it's taken. So if you have a course that's really crucial, but you can't take it until the 7th term, that's going to cause, you know, a lot of issues. And so this is weighting that factor by the term in which you take it. Term is just a subsequent count, you know, first semester freshman year 1, second semester freshman year 2, first semester sophomore year 3. And then what we're really going to be using and comparing is what we're calling this term-weighted curricular complexity. So this is a little bit different than the curricular complexity that I saw when I first stepped into this meeting and Yuming was talking. And this is basically just the sum of these term-weighted course crucialities. And so what we've done here, this all of these courses in this leftmost column are those STEM core for our BSEE curriculum. We have the crucialities. Again, add one to these if you want a direct comparison to the Heilemann longest or Heilemann crucialities because of that difference in longest path. Here are our term-weighted crucialities, and this is assuming that canonical roadmap of degree progression. Our total term-weighted curricular complexity comes out to 737. That's a number that we're going to look at and compare here in a subsequent slide. First time I saw this in Tony's thesis, I freaked out because it's huge, but again, this is term-weighted curricular complexity. And so we're taking into account not just the curricular complexity, but also how this has been organized into a roadmap. So the next thing we did was took our students, and these are our EE majors, our BSEE students. This was IRB approved. Turns out 238 students ended up being incorporated in this analysis. These are students who earned their BSEE between 2008 and 2020. There was a little bit of reduction that happened. It's not every single student that graduated. We needed to make sure that they took the majority of their EE core at NMSU, otherwise the statistics were a bit skewed. But this analysis that we present on the left is for 238 students. And when we're looking at their schedule complexity, what we're doing is we're looking at every term by term by term, what courses did they take? And we use that same analysis. We take the course, cruciality, we multiply it by the term number in which they took it to compute their schedule complexity. Now in this analysis, we're only considering the first time they enrolled in a course, assuming that that was their plan. And so this does not take into account, and this will be some future work, the effects of failing that course, a DFW in that course. But this is if they took the course when they said they take the course, what would their schedule complexity look like? So there's two plots over to the left. The one on the top is basically a histogram for those 238 students of their term-weighted complexity. So this is their schedule complexity. And then this is just count of students. As reference, the orange line here is our canonical complexity, 737. That's the term-weighted complexity. If you were to start exactly where we said, follow our roadmap exactly as it is. You can see quite a spread in the schedule complexity. Now, a couple of things. How on earth can you graduate with a complexity less than the canonical degree plan? Many of our students appear to be coming in with significant credits. Those could be transfers, they could be AP, they could be courses they took from another degree that we are doing exceptions or equivalencies for. This was actually an interesting result because with some of the complications of our current data systems, it's actually really difficult for us to determine transfer credits for our entering students. The green vertical line is the average of this distribution. The standard deviation is about 200, so a very wide range of schedule complexities. The concerning thing for me as an advisor is these people out in this heavy tail towards very high complexities. And future work will have to figure out why, but my hypothesis is they're not taking courses until much later in their degree than they should, according to the degree plan, either due to prerequisite issues, financial issues, something is delaying their ability to take these courses. We also looked at the relationship between these students' term-weighted schedule complexity and how long it took them to graduate. So this plot on the bottom is number of terms. NMSU is on a semester, so we have 2 semesters plus summer. So 3 terms per year. Most students don't take a whole lot of classes in the summer, but especially some of the math courses, which we are including in this analysis, might be in there. So we have number of terms. You can roughly divide this by 3 if you want number of years. And here's the term-weighted complexity of their schedule. As reference, orange is still canonical and green is the average for those. There's 125 students that have ended up above this line. There's 103 who have ended up below here. And we've done a linear fit to these data, which is this red line here. The slope of this is 86.1. Something interesting I didn't notice till I was actually putting this talk together is you'll notice that this red line almost exactly goes through at 9 terms the canonical complexity, and at 10 terms the average complexity. That might be coincidence, but it was just kind of interesting when I was looking at that. If you think about this, slope-wise, this is saying that per term, students are and have a schedule complexity of 86.1. Now, if you look at what they ought to be doing, now this isn't a direct comparison because the term weighted is, weighting things further on in the curriculum, but just if you wanted a rough idea of what does this mean, if you take 737 divided by, the 8, oh, maybe that should be 12 terms, I can't remember. Did I do that wrong? At any rate, you can see that this is on the order of what they should be doing, what the canonical degree roadmap says it should be, but it indicates that they might be taking something a little bit lighter than they should each term. And this is something that we want to look into, both in terms of our curricular design, but also in terms of, could this be a tool that advisors could use when they're looking at student progression? To say, okay, you've been taking this schedule, but it's not progressing you quantitatively in quite the same way. Now, the other important thing to remember is this is in addition to what appears to be significant entering credits. So we have students who are graduating with very high complexities, taking many terms longer than we would like them to graduate, already coming in with many of these courses already complete. So this has opened up a lot of questions for us. This is, as far as we know, one of the first analyses of, what do actual students do in terms of their progression through the degree, and how does that relate to how we planned it for them? If we plan and design the curriculum for a particular curricular complexity, but students aren't following the roadmap for whatever reason, that may, give some additional insight into what's happening there. So the last 2 topics that I want to talk about, all kind of related to a lot of this analysis, are related to grade correlation between courses and topic dependencies between courses. So this is a huge table, and I don't expect you to read all of the details. What I'm going to do is kind of highlight the basics of what we did that resulted in this, and then I'm going to talk about a few specific examples that I think kind of illustrate the potential of some of this analysis. So this is a slightly reduced set of courses compared to the previous. So we're down to 15. Again, these are the 15 we have some more hope of controlling because these are the EE courses. So we have direct decision over exactly how these courses are designed, how the prerequisite structure is organized. So I've kind of color-coded the columns in the table and also the text over here to the right. So these 2 columns in crimson are the courses in our EE core and the pre and co-requisites for those EE core. And of course, that structure is what defines the curricular complexity. We have correlated student grades between pairs of courses in our curriculum. So, for example, this correlation coefficient of 0.63, this is the Pearson correlation coefficient of the student grade in embedded programming compared to the student grade in the prerequisite, which is DC circuits and digital logic. And this is actually a slightly different, and I forgot to put that in in the presentation. I apologize. Slightly different data set, but similar numbers in terms of what we analyzed for this. So this is aggregated over, the population of BSEE students. The blue columns are related to the topic level analysis, and I'll get into some more details on that in a couple slides here. What we're essentially doing here is using topics as a proxy for learning objectives. Ideally, I want this to be learning objectives. Unfortunately, not all faculty design their courses to quite the same level of best practices in terms of course mapping. And so in this initial analysis, topics were the most consistent way we could define our entire BSEE core. And so what we did, and I'll have some illustrations of this, is we basically defined topics. So in DC circuits and digital logic, there's 83 discrete topics. One of them might be, for example, parallel resistance. That's a topic that could be reformulated as a learning objective. Given a circuit with parallel resistors, students will be able to calculate the parallel resistance. And for each of these topics, what we did was mapped it back to which topics do you need to know in order to be successful in this particular topic. So parallel resistance, well, you need to know what resistance is. And so parallel resistance is going to map back to resistance. I'll come back to some of these numbers, and I'll highlight some of these results here in just a moment. So let's first look at this grade analysis. So this plot over to the right is basically a heat map of the correlation between grades. And again, this is analyzed for the population of BSEE students. And it's the correlation between, a course and another course. So obviously correlation course in itself is coming out at 1. A couple of things that were interesting to us. These correlations are all falling within a relatively narrow range between about 0.29 and 0.77. So there wasn't anything that was completely uncorrelated. There wasn't anything that was anti-correlated. There wasn't anything that was, super, super strongly correlated. Everything's kind of falling in this middle ground. As reference, more or less, upper left are courses taken early in their curriculum. As you propagate down to the bottom right, those are later in our curriculum. And these more bold white divisions are by term. So these first 2 courses are taken in the first term, these next in the next term. Unfortunately, there wasn't any structure that really came out of that, but that organization was designed to try to elicit, some relationship. So I want to call out a few interesting examples. And, I've been staring at this for months, and my department head has been staring at this, and we just keep coming up with more questions that would be interesting to answer with this. The first thing I want to call your attention to is these 2 that I've outlined in green here. And so what this is saying is that AC circuit analysis is correlated grade-wise to EMAG and optics at the pretty low level, the lowest level of 0.29, and to semiconductors and electronics at 0.33. But AC circuits is a prerequisite to EMAG and optics and to semiconductors and electronics. So, I went into this thinking, well, the really strong prerequisite, post-requisite structure, those are going to have higher correlations. Obviously, if you understand your AC circuits, you're going to be more successful in electronics. And instead, at least these particular examples aren't necessarily indicating that. Now, what could cause that? Instructor differences. Those could be pedagogical, or it could even just be grade distribution differences. And that's actually something that I've been talking to John about, is can we somehow disentangle instructor differences in grade distributions within this? Could it be just that the few topics that AC circuits introduces that are really necessary in EMAG or in electronics, maybe the instructor is just reinforcing those. Hey guys, remember you have, reactants to deal with when you're dealing with BSEE. Or is there a tenuous relationship between the content? And that's an intriguing question, because this prerequisite structure really drives the curricular complexity, really holds up students in progressing through the curriculum. I'm not saying it's the only thing that should make us rethink a structure between these courses, but it definitely kind of begs the question, why aren't these necessarily more related? Now, a couple of other interesting ones are these ones that I've outlined in blue. These are on the high end of correlation. Linear algebra, probability, and statistics applications, that was correlated with signals and systems 1 at 0.73. And those share a prerequisite structure. So linear algebra, probability, and stats is a prerequisite for signals 1. Now 6 is one of our most problematic, this is linear algebra, probability, and statistics, is one of our most problematic bottleneck courses. It is one of the courses that has the highest DFW rates, the highest number of repeats. And my hypothesis, and partly because this is the area in which I teach, is that the similarity in mathematical rigor, the skills associated with the general mathematical rigor between these courses, is that contributing to the correlation? Similarly, you also notice that multivariate and vector calculus is correlated with the same course, Signals and Systems 1, at the highest correlation that we see in any of this analysis at 0.77. They do not share a prerequisite structure. So the fact that a student has been incredibly successful or not in multivariate and vector calculus has no bearing topic-wise on their ability to go on and succeed or not succeed in Signals 1, but the grades are highly correlated. My hypothesis, again, is that these two courses also share a similar mathematical rigor. And so these grades, I don't think anyone would argue that there's multiple factors in student performance in classes. The instructor, the pedagogy, what's going on the rest of the semester. And so this prerequisite structure isn't the only story here, but it was kind of an interesting analysis. Some surprising things came out of this.
Hey, Laura, it's interesting that AC circuits is low across the board, except for the problem, right? And
Yes.
the multivariate is hot, or excuse me, which one was high across?
Multivariate is 10. It's relatively high, across the board.
Yeah, so like it's just disconnected in general from performance. Yeah, okay.
Yes, and that is something else that we noticed, both Physics 1 and AC circuits seem to be a little disconnected across the board. And that's, also something that we have been questioning.
Interesting.
I should mention this is actually in another paper that was recently accepted in FIE 2021. So further details forthcoming there. So now let's look at these courses and the relationship between these courses instead of student grade correlation wise. Let's back up and look at this kind of in the curriculum sense and in terms of these topics. So this is just a little bit more of an illustration of how I'm looking at and modeling this structure. So we define topics in each course and, completely arbitrary designation for these topics. But, each course has its set of topics, topic by topic by topic in the curriculum. And this was a massive effort of many people for an entire summer. We took those topics and asked ourselves, okay, in order to truly understand this topic, what do you need to understand prior to that? So we mapped, if you kind of focus on this center topic here, we asked ourselves, well, if you need to understand topic 2 in course C, you also need to understand topic 16 in course A and topic 65 in course A and topic 21 from course B. So there's multiple courses and multiple topics can feed in to competency in a given topic. And then this given topic in turn is going to start to feed out into the rest of the curriculum and be used subsequently. So we can map from different courses, or we can even map between courses. Obviously we'd hope that there's going to be a progression through the course and that you're building on these topics. So we have designed and defined this topic map in our curriculum. And as a very, very first analysis, what I'm going to show on the next slide is the following. For each course in our BSEE core, we counted how many times did I rely on any topic from all of the other courses in the curriculum. So, in electromagnetics, how many times did I rely on a topic from AC circuits? I'm going to, every time I counted one, I'm just going to start accumulating that. Now I note, and this is something that we're working on actively now, is this does not distinguish between one topic being referenced many, many times versus multiple topics being referenced a handful of times. And that's one thing that we're really looking to disentangle in subsequent work. But here's the analysis that we get. Now, this is the same set of courses that we saw before. This is a heat map now of counts. And this is on a logarithmic scale because there was such a huge range that I needed to compress the dynamic range a bit here. So just to kind of orient you, diagonals are self-references. So, in any given course, let's take, one of the ones I teach, Signals and Systems 2, right here. There are 290 self-references. So there's 290 times where something I'm teaching in that class needs prior knowledge from something I already taught in the course. Now, you may have noticed, let me skip back here a few slides if I can. The number of topics in each course varied quite a bit. And this is one thing that we do want to look at. I played with some normalizations. I may have to go and play with it again. So it's hard to directly compare course to course. Well, I reference things 290 times and my colleague referenced things, 1,089 times. So clearly he's doing a better job. That's a little harder to directly note here. But these diagonals are self-references. And everything off diagonal, and it's just upper diagonal in this case, the upper triangle, are references to topics in other courses. Now, that could be directly or through a string of dependencies within this graph. So Signals 2 might have referenced something in Signals 1, which referenced something in Calc 2, and we have followed that all the way back and accumulated as we've been going through here. So, we see some obvious things. Our Calc 1 and Calc 2, which are rows 2 and 4 here, are very heavily referenced, probably mostly through these strings of dependencies. So many integrals and derivatives in a lot of what we do. DC circuits, even Signals people, we draw a few circuits up there and talk about, aspects of that. So some of those things were not surprising. Let me call your attention to a few things, and these are related to basically the same courses that we talked about before. So these green courses, those are the same two that we looked at before. Those were EMAG and electronics and their relationship to their prerequisite of AC circuits. So we see that AC circuits is referenced, topics within AC circuits are referenced by EMAG and optics 278 times, and by semiconductors and electronics 317 times. And that's commensurate with how many times there's self-references in these particular courses. So this appears to actually reinforce the fact that AC circuits is a very strong prerequisite to EMAG and optics and to semiconductors and electronics. Now, this is very interesting because remember the grade correlation wasn't particularly strong. And so one of the hypotheses was maybe there isn't, maybe there's a very tenuous relationship between the topics there. Now, again, is it just 3 topics in AC that we're just referencing over and over and over and over again? Or is it multiple topics? And that's something that we're going to look at in future work. Here's the interesting one, I think is the really interesting one. Linear algebra probability and stats applications is referenced by signals and systems 1 0 times. But linear algebra prob and stats is a prerequisite to signals and systems 1. So what's going on here? Now, these are again in my area. I probably should have mentioned at the beginning, I'm a signal processing, image processing, machine learning person. Couple of things that are going on here, and Greg and I were talking about this a couple of weeks ago. If you're a signals person, you say, how can you say linear algebra probability statistics, isn't important in signals? The particular topics that are taught in this course, this linear algebra course, Gauss-Jordan elimination, matrix determinants, basic matrix vector multiplication, those topics are not directly used when we're talking about convolution and Fourier analysis. The other thing that's happening here, and this has not yet been reflected in the course map, the reason why this course is so stubbornly still a prerequisite for Signals 1 is that the lab in linear algebra probability and statistics is where we teach MATLAB, and MATLAB is needed in some of the assignments in Signals and Systems 1. Now, this is a fault of the current course map. This is something that when we looked through the topics, as you would define topics in the course, none of it said, we're teaching you MATLAB this week in lab. And this is where we're going to need to take a bit of a broader look at not just the topics in the courses, but the assignments, and particularly the lab assignments. Now, I still happen to think that this needs to be rethought. And I think that this is an indication of a situation where this sort of analysis can really inform curricular redesign. Okay, so if we aren't relying on concepts, but we need the MATLAB, maybe we need to disentangle MATLAB lab, teach it separately or teach it in another way so that we can make our curriculum more efficient, since there isn't apparently, at least so far, a particularly strong relationship. Another interesting course, I don't have it highlighted, but this one, embedded systems, and also computer architecture, you'll notice are just a straight 0 across the board in subsequent courses. Embedded systems, I don't believe this. I think this has to be looked at more closely. This is where we teach programming for the first time. So this is C programming on an Arduino. Do I ever explicitly in Signals say, hey, remember in embedded systems when you're learning about, no. Do they need to know how to program? Yes. And so, this is going to require a rethought of either our topic map or our curricular structure. The real interesting one is 5, and that's computer architecture. This one, I believe, that it is never referenced in subsequent core courses. It will be needed in specialization courses if you go the computer engineering route. And that's another point of future work is we're just looking at the core. If we look at the core and the concentration electives, does this dependency map change? Are there courses that suddenly become much more important in certain specializations? And again, I think that may inform curricular design. If a computer engineer needs this particular course, they ought to take it. But if the other specializations aren't using that information, maybe we need to rethink, does this belong in our core curriculum? Now, this comes with it's fraught with some politics, and I'm not trying to hurt anyone's feelings associated with any of the topics in computer architecture, so much to say this is what the data is showing in terms of these relationships.
Hey, Laura,
Yeah.
your computer engineering program is a concentration within EE.
It's a concentration within EE, yes.
And I imagine that then they're required to take discrete math.
I don't believe that they are.
Oh, no. Okay. For computer engineering programs, that is a requirement.
Yes.
And computer science as well. And this problem that you mentioned about like linear algebra, the actual topics taught by the math department in many cases don't align with what you need to do in the applied course. I think the same thing. I hear that all the time from students who take discrete math, and then they come and take an algorithms course, and what we need them to know from discrete math and algorithms, they learned other things. And
Yes.
so there's a disconnect, or like it's an impedance mismatch or something that takes place that I think that would be another interesting one to investigate.
It definitely would be. And I should preface this by saying, I don't know much about our computer engineering concentration. It's probably the furthest from, my particular areas. The one that I like to talk about, because it's my pet peeve, is partial fraction expansion. And so, I teach signals and systems too, and we're talking about Z transforms, and I say, do the partial fraction expansion, and my students go, and I say, you learned that. And then I teach it to them. And so when we all sat down to do this course map, it was me and some other faculty and graduates of our program, either had graduated or were about to graduate. And I said, okay, y'all, when did you learn partial fraction expansion? And they said, from you, Dr. B. And I said, no. When's the first time you learned it? When did math teach you? And it was kind of this, deer in the headlights. John might have a different record. I think John and I finally figured out where we thought it was supposed to have been taught. But that's my, discrete math issue, the analog of my discrete math issue. And I've kind of just come to the realization that I need to just take half a lecture and teach partial fraction expansion to the extent that my students need to know it for Z and Laplace transforms. But it's also something that I had been assuming for 8 years, that my students knew this coming in. And I think those sort of things, either the discrete math issues for computer engineering or, my partial fraction battle, are things that this can also quantitatively demonstrate. And so I'm going to conclude actually with a whole bunch of questions, and these are kind of the questions that have been percolating through my mind as I've been working with Tony and John and Irving and others on these analyses. Related to student schedule complexity, can we use this as a tool to help guide students? Can students use this as a tool to understand the impact of choices that they make? When I advise students and I say, you really ought to take Signals 1 next semester, and they go, oh man, that's a hard course, I'm just going to take it next year. Yeah, you can do that, but that's going to have an impact on electives. And lo and behold, next year they say, I'm going to take DSP with you. And I say, not till you're through Signals 1 and 2. There's implications to some of these choices. And this could be a more quantitative way of reinforcing that. I'm really interested, and this is something that Tony is probably rolling his eyes because I slacked him about this earlier, but how do DFWs affect student schedule complexity? Our DFW rates are a huge concern in many of our courses for student progression. Could this provide another way of measuring the impact of not passing a class? Grade correlation, we already kind of talked about, can we disentangle instructor grade, other compounding effects? The course dependency map, some active areas that we're looking into, and I have some ideas on are which topics are referenced the most often. That can be used to define a more efficient curriculum, that can be used to guide more persuasive arguments like this course should not be a prerequisite to this particular course. And can we use that information to promote student success, which leads me into my last bullet, which is if we know topics and how they affect subsequent understanding and competencies within the curriculum, we could flag students early. Okay, you're struggling with limits. If you don't understand limits, you're not going to understand derivatives, you aren't going to understand integrals, you aren't going to be able to do AC circuits, that's going to propagate. And if we have this relationship between topics, can we focus our attention a little bit more? What assignments need to be beefed up? What assignments need to be scaffolded better? What assignments maybe do we need to flag some interventions with students? And then the last thing, and this is something I've been interested in for quite a while, we have arguments about this as faculty. The default is get a C- and you've passed the course and you can continue to the subsequent courses. Is that really promoting student success? Not that I want to hold more students back, but is a C- level of competency really going to propagate to success in subsequent courses, or do we need to rethink? We need to be more stringent in our progression of students into the next courses and provide them with resources to become successful in those topics, because those are the topics that are most important. So I'm going to leave it here. Hopefully I gave you kind of an overview of some of the work that's going on here, and happy to answer any questions, or if anyone had any thoughts on this, happy to entertain a discussion.
Hey Laura, this is Shawi. So very, very cool work. So
Thank
can you go back to the one on the topics where you had the graph?
This one?
Right here. Yeah, yeah. So one thing strikes me here. First of all, I think so you can look at these, and especially what you said you want to work on, look at to see if a certain topic is illustrated or is being used more than, referenced more than others and so on. So you can look at this by the, basically look at the in degrees and the out degrees of a particular one, right? So if you look at that, you can get a lot of information about, the distribution of that. For example, you can look at topic 2 and you say, in this case, it looks like it has an in degree of 3. Now, there's a complication in your analysis, which is, it could be that, so topic 21 maybe depending on something else above it, and that you're counting that too. So I think you may, and you said you may want to disentangle this and see if that's the case. I think it would be interesting to see it from a graph theoretic stuff, and I think you'd be able to just by maybe even just do analysis on the distribution of those degrees to see something from it.
Yeah, that's a great idea. Thank you.
And the last thing, if you go to the last slide, also when you said something, but so that question about the C- or as you know that there's software right now, for example, that go topic by topic, in math in particular or others, and you have to do a 90 or above in a particular topic in order to progress. So since you do have it done by topics at this point, I think you can probably also do some analysis on that to see, okay, what level, what you're asking is I think an extremely important question, which is, when you say C- in a course or even a B in a course, you may not have tested on all the topics, right? You can get a B, but you have still a gaping hole in your knowledge on some topics, which are what you needed. So I think getting to the topics, or to the learning objectives ultimately is really the way to do it, because, a B is you're getting, or a C-, it could be that you got tested on the topics, you're fine, whatever, maybe that's not really hopefully the design of the test is really capturing what's most important, but that's not always the case. So anyway.
Yeah, absolutely.
All right, cool.
Thank you.
Mm-hmm.
I was going to bring up while you're on this slide, the course dependency map. Can that information be used to redesign a more efficient curriculum? This is kind of the topic of Yiming's work, I would say. And so this, and he'll talk about that next week. What he's looking at is, can I put as many topics together? So you have this self-referencing of topics within a course. So the optimization algorithm he's going to talk about is, can I put as many of those and self-contain them as possible so that, you don't get in this situation where if you don't pass a course, you can't take the next one. So the huge issue here is collecting all those, we've got them as learning outcomes, you have them as topics, but I think those are pretty darn close to one another. And I'm just wondering, Yiming has done work in getting the topics for a EE program, believe it or not. So I suggest that maybe this week, if we could get our students together, they could share like your topic graph and we could share our learning outcomes graph. And at least I think there's probably some reconciliation that would need to happen between them. But it would be kind of interesting to start to work on, maybe there's a standard set of topics with a EE program that we're kind of capturing with this, and we might be able to do something interesting working together. So maybe Yiming can get together with somebody on your side this week.
Sure, yeah. So let's see, John and Irving are probably most familiar with the course topics. Tony, did you helped write those up that summer? How comfortable are you with those? Is Tony still on? I can't see.
Yeah, I'm still here. Yeah, I've not really done any work with them, so I'm not extremely comfortable with them, but I'd love to sit in on the conversation.
Well, I'll have, like, Laura, if you want to just give me the emails, I'll put them in touch with Yiming. I think it would be interesting to just share some of that data because we might be able to help one another there.
Yeah, definitely. I'll send you their emails, and then Yiming can, correspond with them offline. And, I'm happy to jump on another meeting in the future if we wanted to.
Yeah, I think, well, he'll talk this coming week, so I'll send you all the.
Yeah, that would be great.
And then Hussein, who is on the call, I don't know if he's still on, but he's kind of looking at what level of performance, is predictive of levels of performance in subsequent courses. And he's using a little bit different approach. And I think he's scheduled to talk in 2 weeks. In 2 weeks. So it's related to this as well, but I think we were thinking about things a little differently. So I think this might be interesting to share some of that.
Yeah, definitely.
Does anybody else have any other questions?
I have a question. So, okay, it's fine. So can you go back to a slide with a table which shows a number of topics and the dependency topics? Yeah, I guess this one. So let's see. So for the left column, number 5, computer architecture, and we can see in the fourth row, which is called topic dependency, right? And my question is, why do you have a 0 here? So since it's a dependency topic, why do you have a 0 here?
So in this particular case, computer architecture, which is VHDL and some other things, that it's been so long since I took a computer architecture course. What this table is saying is computer architecture, we found 44 discrete topics within computer architecture. And within computer architecture, it referenced topics in DC circuits and digital logic 28 times, and topics from embedded programming 0 times. And embedded programming is C programming on an Arduino. And so I think what's happening here is that since computer architecture is VHDL and more focused on design of an organization of computers, that there just isn't that relationship. And I'm not going to die on the hill of there are no topics, but there wasn't any obvious relationship there that we saw in this first pass.
But embedded, it is a prereq though. Okay.
It's a co-req.
Those are correct. Okay.
It's a co-req. Yep.
Well, it's a co-req, but with 0 topic dependency.
Yes, exactly. It's another place where we might want to rethink, is it necessary that you be enrolled in or completed embedded to take computer architecture?
And what does the dash line underneath 0?
Yeah.
It means not applicable?
So technically, computer architecture has a prerequisite of trig and pre-calculus. That is not part of our BSEE. That's a competency that we assume prior to starting the BSEE. And so we didn't map anything in trig and pre-calculus because it's not part of the core here. So that's basically saying we don't have anything to report in terms of this relationship.
Okay. And how do you define the prerequisite for the dependency topics?
So the prerequisite comes from our BSEE. Well, I guess I can stay on this. So these pre and co-requisites come from our degree plan. So within our curriculum, you have to have taken DC circuits before you take embedded programming. That's just defined in our catalog. And now if you're asking in the broader sense of how did we decide that that's supposed to be a prerequisite, is based on, I would say, a high level thought process. You know, for example, linear algebra, prob, and stats, of course, that's important for signals. And we teach MATLAB, so we're going to make that a prerequisite for Signals and Systems 1. Now, these have also kind of tended to be inherited from curriculum to curriculum, from catalog to catalog. And I think there's some drift in the curriculum that the prerequisite structure has not necessarily caught up with. Now, I believe that the thought process in embedded programming being a prerequisite to computer architecture is that embedded programming is potentially the first time students have seen programming, period. So our thought process is, well, if you're going to be talking about how to design a computer and VHDL to model the computer, you ought to know a little bit about programming. So we'll make it a co-requisite. You know, that's the kind of thought process that we have. And I'm not saying there's anything wrong with that, but maybe it requires some rethought there.
Yeah. Interesting.
And this is also, you know, a curriculum designed by a committee. So just like a camel is a horse designed by a committee and comes with its own issues, you know, we definitely have some things here. My hope is that myself and my colleagues being a bit more quantitative minded, that this sort of analysis might make some inroads, where if I just went to a faculty meeting and said embedded shouldn't be a co-requisite for computer architecture, they'd say, what are you talking about? You know, whereas this might lend a quantitative, objective measure to it.
I was going to mention real quick, Laura, just for your, you know, when we define the delay factor, so the longest path between a source and a destination is the number of edges on that path, and what we wanted was a singleton course to have a delay factor of 1, and so that's why we say, well, let's pick the number of nodes on that long. So the actual definition is the number of nodes on the longest path.
Right.
But that was why we did it. Maybe there's a better, again, these are just made up things, so maybe there's a better definition of that, but that's what we
have. And it makes complete sense. And it was one of those things where I was so happy to have found the command that did longest path that I forgot that I was supposed to add, I mean, in all honesty. And so
the number of nodes on that path, so that's
right.
One more than the number of edges, unless you've got
unless, I mean, for a directed acyclic graph, I think it's always just going to be one more will be the number of nodes on there. So it's an easy correction, and we'll probably make that correction going forward. But it was like 11th hour of the FIE deadline. Oh, Tony, I'm so sorry. I forgot that.
Anyways, that's why we wanted it to be, it to be 1. So anything else? We'll get out an abstract for Yiming's work to you all like early this upcoming week. And we'll same channel, and we'll try and get a website put together in the next couple of weeks for all this. So, and again, Laura, you're welcome to attend if you would like. It's up to you. This kind of an
sure. If my schedule permits, I definitely would be happy to.
Or students, whatever.
Yeah, definitely.
Shawi, did you have anything to add?
Nope. Very nice. Thank you.
Yes.
Thank you. And thank you for inviting me. I appreciate it.
Well, thank you for sharing. Everyone have a good weekend.
Take care.
Thanks, everyone.
Let me see. Jachin, Bethune, see you guys.